Okay. Good morning, guys. My name is Mario Pesca. I'm an engineering student at Central Queensland University, and this presentation is about my final year project based on flow modeling through an electrostatic precipitator to capture microparticles. First, I would like to give you guys a little bit of an idea of where this presentation is going to go. First, I'll explain why we chose this project and how it fits the engineering box. It'll be followed by some of the overview work carried out during the planning stages and some of the aspects of the implementation. And then I'll briefly explain some of the methodology and the results obtained, followed by some suggestions for future work, and finally there will be time for some questions. So in 1991, an American study showed that a pulverized coal boiler produces about 25 ton fly ash per hour. That's equivalent to 200 ton per year. If that gets taken and deposited at sea level in front of the Sydney Harbour Bridge, it will immerse the bridge in 4 years. So the international environmental regulation continued to limit the emission of micron and submicron particles. The reason why is because those smaller particles they got higher probabilities of deposition in deeper parts of the respiratory tract. So the EPA proposes to categorize coal ash as a hazardous waste, creating a federally enforceable requirement for ash management, including waste management, transportation, and disposal, calling for actions to be taken before the operating companies get affected by the new regulations. So this project allowed me to seek knowledge through research, creative design, development of strategies and solutions, while applying concepts of fluid mechanics and dynamics to describe the study scenario. The requirement to carry out modeling and simulation to understand the phenomena taking place, resulting in developing of predictions and rapid prototyping, time and budget saving practices, while considering sustainability and environmental regulations. Now, the aim of the project was to investigate numerical modeling of the flow phenomena of fluid particles in an electrostatic precipitator. Some of the work carried out during the planning stages allowed me to define the project scope, identify stakeholders, and develop the required work breakdown structure, risk assessment, and also develop a project plan, which had to be modified several times in order to meet the project deliverables. Now, an electrostatic precipitator is a large industrial emission control unit designed to trap and remove dust particles from the exhaust stream of an industrial process. It has many advantages compared to bag filters and cyclones, mainly due to the wide operating temperature range and the high collection efficiency. It has several problems as well. It is massive initial capital investment, high operating and maintenance costs, large occupational area, and low collecting efficiency of smaller particles. Now, the ESP is based on electric field formed between the discharging electrode and the collecting electrodes, and the potential difference that ionizes the surrounding fluid. This potential difference induces the Coulomb forces to act on the floating particles, pushing them towards the collecting electrodes, where those charged particles are then trapped, and then they get dislodged off by a process called wrapping. Then they get induced into a number of hoppers depending on the size of the electrostatic precipitator, and then they get transported to either be retreated or to get disposed of. As mentioned previously, one of the main drawbacks of the ESP is the high initial capital investment. The phenomena occurring in the ESP is extremely complex due to the interaction of fluid flow, electrostatic force, and particle motion. Therefore, to predict the flow, behavior, and the performance of the fluid inside the ESP is a complex task. So we can do this either experimentally, theoretically, or computationally. To do this computationally, we use CFD. So CFD is a complex tool, but allows us to visualize and analyze the results of possible solutions and particular cases, supporting decision making and avoiding potential consequences of trial and error practices. So we can see the complexity of the behavior of an electrostatic precipitator, where we have materials belonging to a primary phase, which envelops the secondary phase, which is distributed through the continuous phase. The flow could be laminar or turbulent, which results in a variety of flow regimes for multiple phases, and they all interacting within the same channel. Now, we can see some of the work carried out during the implementation stages of the project. As the phases of the model coexist, there is an interface coupling due to drag, lift, and other forces, resulting in an exchange of moment and energy. This exchange takes place between the continuous and the dispersed phase, and it is accounted for using the Eulerian and Lagrangian framework. Once we defined the method and the geometry base was completed, the development of the mesh was required. It required us to use a hybrid approach with triangles, wedges, and hexahedron shapes, in addition with sizing and inflation layers to better capture the behavior of the flow. Now, in order to start the simulation, we had to define the appropriate boundaries, having the outlet at atmospheric pressure, the discharge and the collecting electrodes as walls, and the inlet at 7 meters per second, resulting in Reynolds numbers of 10,900 to 232,000. The dimensions of the channel were highlighted in the report and were based on previous research. So at this stage, we were already using Fluent. ESP presents multiple phase flow with transient particles, and therefore we use transient simulation in order to account for those variables changing with time. The first model was a flat plate electrostatic precipitator with a 3 electrodes configuration displaying a slight pressure drop, which was found to be a normal operating characteristics of the electrostatic precipitators. On this model, we use square baffles to represent the corrugation on the collecting electrodes, increasing areas of low velocities for individual channels, which is then multiplied by the number of channels in the precipitators. Then a change of geometry was imminent, since the square baffles also introduced parasite drag. Now, based on Bernoulli's theorem, the introduction of convergent and divergent baffles were considered as a solution due to the angle of attack being able to affect the behavior of the flow. Now, as we proceeded with the mesh analysis, the main problem that I encountered during this project was faced, which was that the student license only allows me to do 512,000 cells, where my research highlighted that I was going to need at least 2 million cells in order to simulate an electrostatic precipitator with discharging and collecting electrodes. So the model had to be discretized a little bit further, and now the flat plate is displayed on a 2D scenario. As you can see, it displays a Bank-Herman effect as a result of the flow over the discharging electrode. And the square baffles were modeled to display a low velocity regions close to the collecting electrodes and a high velocity at the fully developed region. The new geometry increases the velocity gradient, and the vorticity is induced due to the variable stagnation pressure and the flow separation. With the convergent baffles, the areas of low velocities are still present due to the no-slip conditions selected in fluid. Now, some of the particles seem to be traveling at lower velocities along the channel. However, the velocity increases significantly along the center of the duct, which may affect the performance of the precipitator. With the divergent geometry, it presents an initial abrupt change of the streamline and adverse pressure difference that may affect the performance of the first baffle, but then the second and the fourth baffle efficiency seems to be increasing. I was expecting an evident result with this geometry due to the divergent geometry, but the results obtained weren't as meaningful as I was expecting. Now, with the optimized model, we aim to maintain low velocity regions, and the difference between the models lies in how much disturbance will be present for the smaller particles or for the particles that already lost their charge. So the combination of the 3 models allowed to put together the geometry in which the drag generated was maintained low, and the proportion of the baffles were maintained at 1:1, 1:2, and 1:3, obtaining optimistic results for the efficiency improvement of the ESP. The airflow velocity increases as it overcomes the first baffle. The static pressure decreases and transforms into kinetic energy. The longer the ratio, the less the kinetic energy, and then the less the kinetic energy transforms into turbulent energy, and the less chances for particles re-entering the airflow. Now, the turbulent kinetic energy is of lower magnitude for both geometry ratios and lower than the initial models. However, we still have some eddies, which again will produce some risk of particles re-entering the airflow. Now, the new geometries are based on the original square baffle. They present a leading edge to trailing edge ratio of 1:1, 1:2, and 1:3. The convergent region allows the boundary layer to become thinner as the accelerating fluid is maintained close to the wall. and then remains stable. Once it reaches the top, the flat section allows it to stabilize momentarily, and then the divergent region experiences a thicker boundary layer, and the angle of the slope determines how unstable the flow becomes. Turbulence enhances diffusivity of the model. Therefore, at greater turbulence kinetic energy, the transfer of mass, momentum, and energy is increased. Our geometries display lower turbulence and kinetic energy, hence the less resistivity and reduced moment, and therefore an increase in residence time, resulting in electrostatic forces overpowering the kinetic energy left in the particles and pushing them towards the collecting electrodes, where the process can be continued. Now, at this stage, it must be added that in order to assess the effectiveness of the optimized geometries, the incorporation of secondary phases is required. Nonetheless, assuming that a high applied voltage and large particles were considered, the geometries highlighted are considered an optimal for dust collections. Now, our model developed good predictions of flow distribution inside the electrostatic precipitator. Those results then are encouraged to be applied and compared with results obtained in a laboratory scale electrostatic precipitator. Additionally, a multi-phase flow incorporating an electromagnetic field is encouraged, since some research points out that favorable results as a consequence of electromagnetic fields acting inside the chamber, due to the smaller particles being brought back into the corona discharge region, allowing them to regain their polarity. And finally, this report was based on a power generation industry. However, the optimized geometries could be applied to automotive, hospitality, and chemical industries. Now we have some time for questions.